Hello everyone. In the last session, we looked into the stiffness matrix of the frame element, the relation between local and global stiffness matrices, and the concept of transformation matrix to obtain the relation between global stiffness matrix and the local stiffness matrix of the frame element. And we also did a numerical where we solved a simple frame using the transformation matrix. Now today we're going to learn about a very important concept in finite element analysis, which is the shape functions. Shape functions are the fundamental tools which are incorporated in the finite element softwares like SAP or Abacus or ANSYS, which allow a quicker processing of the complex problem. Since we are engineers, not mathematicians, we generally have to find an approximate solution to our problems. For example, if you have beam like this and you have loading here, then the beam is likely to bend like this. Now, while solving this, we may not require to find the exact location of these points, these deflected points under load P. We may be satisfied with a solution which may look something like this or something like this. Therefore, we have to find a solution which is accurate enough to design something. If we want to obtain the exact solution on this one, then you'll require a lot of nodes or elements. Now what this does is you'll have more nodes. Now this results in having more elements. Then you'll have more local matrices, and while assembling them you'll have a very big global stiffness matrix. Now if you want to solve this, it's going to take a longer time, and memory as well. Therefore, we generally have to find a balance between this and our accuracy, and this is where the concept of the shape functions arise. Now here we have a cantilever beam like this, and this is likely to deflect like this under this loading, and let's say we only have two nodes here and here. So this is a single element, which means that it only has one local matrix, which will be equal to its global matrix. Now while solving this, you'll only obtain U1, U2, U3 and U4 at these ends here. But what you really want to do is you want to find your deflection, let's say about this point here. Now how do you do it? One way of doing it is we add a node here, add a node, and we form two local matrices, K1 and K2. If this is element 1, element 2, then we'll add it up and then we'll obtain our global stiffness matrix and solve it. Now you see the problem here is that we increased our complexity. Now what shape functions allow us to do is they allow us to approximate this deflection here. If we assume a curve or approximate the solution like this, which is linear, then what this will do is that this will allow us to approximate these points which are at different location between this point and this point. Now you see the solution we are looking at, let's say this is point C, then you'll get solution here rather than this. So this will be your exact solution, while this one will be your approximate solution given by your safe function. Or if we assume a safe function to be like this, let's say this is a quadratic curve, then this solution may provide a closer solution to the exact one. Therefore, safe functions are the approximations to the deflected shape of the elements under certain loading condition. For example, you can have a bar element like this with loading. You can have displacement in these directions like this. Let it be u1, u2, then u1 you can have it here, and u2 you can have it here, and this may be your safe function. Here the displacements are in horizontal direction, but I have just plotted in the vertical direction just to show you that it is linear. So therefore, these safe functions come in very handy when we want to approximate a solution at a certain location in a beam or a bar element. Now the accuracy and the complexity of the solution depends upon the assumed safe function. Now let's do a simple example of a bar element where we are going to obtain its safe functions. Let's say there's a bar element here and we have applied load P. In our bar element will have 1 degree of freedom here and another degree of freedom here. Let this be u1 and let this be u2. And after solving this, what you'll get a value of u1 and u2. Remember that you have already solved the problem and you have obtained your solution. Now if you plot this in a graph, what you'll have is, let's say this is point 0, this is L. Now this is your x-axis and this is your displacement u, which is a function of x. Now let's say your solution at x equals to 0, which is this point here, is u1, and at x equals to L, which is this point here, is u2. We can assume a safe function like this, which is linear. Now the equation of this one will look something like ux equals to a naught plus a1 x. You see that this is a linear equation. In this condition, we have two unknowns. Now these unknowns depend upon the degrees of freedom you have, and we have to solve for a naught and a1 depending upon your boundary conditions. Here the boundary conditions are, at x equals to 0 you have your u, 0 equals to u1. Now your u0 will be, if you put 0 here, you'll get a naught plus a1 times 0 equals to u1. Therefore your a naught equals to u1. Again, your another boundary condition is x equals to L, where your UL, which is this point here, you'll get equals to U2. Now you can write this as A0 plus A1L equals to U2 when you substitute L here. Now here you'll get A1L equals to U2 minus A0. Your A0 is U1, or you'll have your A1 as U2 minus U1 divided by L. Now this is your A1 and this is your A0. Now when you substitute these values back into this equation here, then what you'll get is, now you see this equation here is in terms of x. This is a function of x. Now what we'll do here is we'll rearrange this, and what we'll get is, the reason we are doing this is we want to write this in a matrix form, because what we would have done earlier is that we would have obtained our displacement solution in this form, which is the vector form. So we can write this one ux, which will be a vector, equals to, you can write a matrix here, which will be 1 minus x by L and x by L, and then you'll have your u1 and u2. Now this matrix here is the shape function matrix, which is generally denoted as N matrix. This shape function matrix is specific to bar element. You'll see that this and this are dimensionless, and if we denote, let's denote x by L as S. Now you see, if your x equals to 0, then your S will also be equal to 0, and if your x equals to L, you'll get S equals to L by L, which will be equal to 1. Therefore S varies from 0 to 1. Now you can write this as your shape function as 1 minus S and S. Now you see here what this did is it normalized our displacement values between 0 to 1, which is easier to handle. These are known as natural coordinate systems. Now there is another natural coordinate system which varies from -1 to 1. This is the xy coordinate system. Now here you see that if S equals to 0, we should obtain xy equals to -1, and if S equals to 1, we should obtain xy equals to 1. Now you have to find a relation between S and xy. Here your S equals to 1 plus xy by 2. Now you can substitute this here, then you will get your shape function matrix in terms of xy. You can write here 1 minus 1 plus xy by 2, here 1 plus xy by 2. Now this will turn out to be 1 minus xy by 2 and 1 plus xy by 2. Now this is in function of xy, this is as a function of S. Generally what happens is that, except for the beam elements, because they have different dimensions of their degrees of freedom, which may be rotation and displacements. But in cases like bar elements, the sum of your safe functions is generally 1. For example, if we add these two up, you should get 1. Which will be equal to, another property of the safe function is that if you have a bar element like this is degree of freedom 1, this is degree of freedom 2. Now each degree of freedom will have its safe function. For example, here the safe function of this one can be considered as n1, which will be equal to 1 minus xi by 2, and safe function of this one can be considered as n2, which will be 1 plus xi by 2. Xi here is equals to minus 1 and xi here equals to 1. Then your n1 at this location here will be 1 minus 1 by 2. This equals to 1. This is another property of the safe function. And if you look at your degree of freedom 2, then your n2 will be given by 1 plus, now this is equals to 1 by 2, that equals to 1 again. And if you are looking at the value of your safe function at other degrees of freedom, for example, you are trying to find your safe function n1 at your degree of freedom 2. Now at degree of freedom 2, your xi equals to 1. Therefore your n1 at 1 will be equal to 1 minus 1 by 2, that equals to 0. And let's say you are also finding your safe function of degree of freedom 2 at degree of freedom 1, xi equals to minus 1. Then what you'll get is n2 minus 1 will be equal to 1 minus 1 by 2, that equals to 0. Therefore, your safe function values for the corresponding degrees of freedom will be equal to 1, and their values at other degrees of freedom will be equal to 0. So this is another property of the safe functions. I'll show you one of the advantages of having the safe functions. We know that our strain is a derivative of displacement with respect to x for the bar element, or this equals to your change in length divided by your original length. Now this is average and this is our instantaneous. Now let's find du by dx for the bar element. Now you see your ux is this one here, so you can write it down and you have to find the derivative of all of it. So what we'll get is, this is constant, so you can take this out, and this one you have to bring it in. So what you'll get is, now let's open this, let's see what you get. Now what this is showing us is that if the displacement at this point is u1 and this point is u2, then the difference between these two is your change in length, that is u2 minus u1, and your L is the initial length. Therefore this will be equal to your delta L by L. Now this is giving us our strain in the element. Now the matrix here, this one is known as the B matrix. Now your B matrix will look something like this. It will be a derivative in terms of x, or it can be in terms of s or xi of your safe function matrix. In the above solution, you can see that we obtained our a1 as u2 minus u1 by L. Now we can see that this equals to our du by dx, which is the slope of the line. So they do have a meaning. Now this is our strain component and u1 is our initial displacement. Now you can see that we can solve for our strain or our stresses in matrix forms. Let's look at another example. Now if you move into like 2D elements, let's say we have triangle element that looks something like this, and our triangle element, let's say, has 3 nodes. Let this be node 1, this be node 2, and this be node 3. Let's label this one as A, this one as B, and this one as C. Now in 2D element, what happens is that you'll have 2 degrees of freedom at each node in X and Y direction. Let's say we solve this problem and we obtained our solution, X1 and Y1 as our solution, and here let this be X2 and Y2, and this be X3 and Y3 under certain loading condition. Remember that we have solved this problem already and we obtained our solution. Now these are our solutions. We just plot this one in the graph. This is your solve point 1, this is your solve point 2, this is your solve point 3. Now this one corresponds to X1, Y1, this one will be X2, Y2, and this one will be X3, Y3. The problem here is that we only know the displacements at 1, 2, and 3. But we like to know the displacement at a point somewhere here. Now you're going to find this one using shape functions. Since there are 3 nodes, there will be 3 shape functions. Let it be n1, n2, and n3 for our nodes 1, 2, and 3. This point, let it be O, x, comma, y. You want to solve for that. Now let's say your x equals to, as you saw before, we write our equations in terms of shape functions. Now what we'll write here is n1 x1 plus n2 x2 plus n3 x3. That's your first equation. And then you write your y in terms of natural coordinates as well. y1 plus n2 y2 plus n3 y3. And these are 2 equations. And there are 3 unknowns. Now the final equation can be obtained by using the property of the shape functions. Now the property for the shape function is that you will have n1 plus n2 plus n3 equals to 1. This is our third equation. Now this is the property of the shape functions, that they will all add up to be 1. Now we have 3 equations and 3 unknowns. Now if you write this in matrix form, what you'll get is, now to find this one, we have to take this to this side. So your shape functions vector will be equal to, from the mathematics, the area of a triangle is given by half of the determinant of these coordinates. Now this will be, now this determinant will be this one. Now if you write the area as delta, then what you'll have is, you'll have your determinant as 2 delta. Therefore we can write this as 2 delta. Therefore, what you'll get is, let's say this is matrix M. So we'll have matrix M 1 by 2 delta times U vector. This is our safe function for the degrees of freedom for the 2D plate element. Yeah, let's find the inverse matrix. This M matrix will be adjoint of this matrix here. Now the adjoint of matrix is the transpose of cofactor matrix. Now the cofactor matrix is given by minus x2 y1. This is the cofactor matrix. If you want to find more on cofactor matrix, please look at it yourselves. And now we have to find the transpose of this one. Now the transpose of this one means that we exchange rows and columns, x2 y1. Now this is our adjoint matrix. Now this is our matrix M. Now the easy way to find this matrix, when you look at what we're solving here, now we're solving for n1, n2 and n3. Now you can see here that in here degree of freedom 1 is missing, here degree of freedom 2 is missing, and here degree of freedom 3 is missing. You can generalize this one in a form. You can write here L1 M1 N1 L2 M2 N2 and L3 M3 and N3, where generally you'll have your calculator with you, so you actually don't need to find these values. You can directly find the inverse of this matrix easily using your calculator. So this is just a derivation of our general solution. This is how we obtain our M matrix, and this is our safe function right here. Now once we write this in this form here, and if we open that part, what you write here is, now what this solution is saying is that when you have a triangle, for example the triangle we had before, now let us draw a line that joins these points here. Now if you look at our first equation, if you look at these values here, they only consist of node 1, node 2 and node O, which you are trying to find. What this is giving us is the area of this triangle here. You can do your calculation yourselves and you will find that that equation gives the area of this triangle. That's for this triangle here. And then when you look at the other equation, second one, you know that this consists of coordinate 1 and 3. So this will be giving us area of this part here. So this is for the second one. And for the third one, this equation here will be giving us the area of this triangle. This will generally be 2 times the area. So if we denote this one as delta 1, this one as delta 2 and this one as delta 3, then what we'll get here will be 2 times delta 1 by 2 delta, and then 2 times delta 2 by 2 delta, and 2 times delta 3 by 2 delta. Now when you cancel these out, what you'll get is delta 1 by delta, delta 2 by delta, and delta 3 by delta. Now you see the safe functions here are the ratios of the subtriangles inside found by the location you are going to find your solution divided by the coordinates. Let's check the properties of our safe functions. Now we have our first property that should match is n1 plus n2 plus n3 should be equals to 1. Now if you add those up, what you get is now delta 1 plus delta 2 plus delta 3 is the whole triangle. That means it is delta by delta that equals to 1. Now this condition satisfies. Now let's look at other condition. The second condition is that let's take safe function for our coordinate 1. Now we have n1, and let's find the value of n1 at 1. So at the rate 1. Now for this case, your point O moves from here to here. Now if you make a new triangle, now this is our original triangle like this. Now your point O shifted from here to here because we are trying to find our value of n1 at 1. So this is our O now, x comma y. Now you see that when you move this one here, you see the area, this whole area will become blue. It's like elastic band. When you have, it is like stretching a band here. Let's say these all are elastic bands. Let's say if these lines are elastic bands, then when you pull this band here, you see this one consists of 1 and 2 and O. That means this is delta 3, this is delta 1, and this is delta 2. Sorry for my mistake. This part, your color, when you pull the elastic band from this point to this point, all of this section will be, so you see the whole area will now become delta 1, and now this delta 1 will be equal to the area of this whole triangle, which will be equal to delta. So your delta 1 by delta will be equals to delta by delta will be equals to 1. Now the other condition is that your n1 at the rate 2 must be equal to 0. You see that when you move this point to 1, it stretches, and you see that your delta 2, which is the red color, is not visible. So your delta 2 will be equal to 0, and you will have divided by delta, so this will be equal to 0, and your n1 at the rate 3 must also be equal to 0. You can see here there is no blue color. That means your delta 3 equals to 0. Now divided by delta, this will be equals to 0. Now you see this condition also satisfies. Now once these conditions satisfy, you'll know that your safe functions are correct.